So I'm Zheng Wang from University of Edinburgh. Today I'm going to present a joint work that is collaborated with my colleague Dominic Gru and Michael Boy. So in this work, we develop a compiler to automatically generate efficient OpenCL codes from OpenMP programs, and at the same time, we use machine learning techniques to develop a model to predict whether the CPU or the GPU on your system should be used to give the best performance. So this work is motivated by the fact that GPU programming has become mainstream. The NVIDIA Tesla or the ARM Mali provides thousands or hundreds of cores, making them very suitable for highly parallel tasks. The OpenCL is becoming the industry standard for GPU programming. Although OpenCL can also be used for CPU or other type of systems, such as FPGA, currently people mainly use OpenCL for GPU programming. The problem with OpenCL is that the OpenCL is still a low-level program language. Programming with OpenCL is not very easy. And the problem associated with that is the application may often need to be rewritten or retuned if we want to target new processors. This means a lot of effort has to be put in if we want to get a good performance for different processors or the new release of different architectures. So the goal of this project is to try to bring together the benefit of a high-level program language to reduce the overhead of developing program, and at the same time to use OpenCL to explore GPU performance. We choose OpenMP because it is a high-level program language, very easy to use, has very little information about, has very little architecture-specific information, and can be targeted for different architectures. So the idea is the developer uses OpenCL pragmas to express parallelism, and our compiler can automatically generate efficient GPU codes from the OpenCL program. So whenever we want to target our program for new GPU architecture, we can rerun the automatic translation process, and hopefully the compiler will automatically generate efficient code for the new architecture for us. So before I talk about my techniques, I would like to discuss the difference between the CPU and the GPU. So although GPU program is pretty trendy at the moment, not all applications are suitable for GPUs. Here I give some of the characteristics that are important in terms of determining the task mapping between the CPU and the GPU. So if we look at the parallelisms, the GPU is more suitable for highly parallel tasks instead of sequential or modest parallel tasks. If we look at memory access, most GPU applications have regular aligned memory access. This is in contrast to many CPU applications, which may have irregular and indirect memory access. If we look at control flows, so many GPU-friendly applications have a regular control flow, has only a few branches. However, many CPU applications may have irregular control flow and many branches. So the takeaway message here is that the GPU is not always the best fit for applications. There are applications cannot run on the GPU at all. And even for those applications can be run on GPU, the GPU is not always outperform the CPU. So there's a boundary between the GPU-friendly application and a non-GPU-friendly application. However, knowing the boundary is pretty hard. It is hard because the parallelisms, memory access, and control flow, they are all depends on the program itself, depends on the program inputs and the underlying architecture. So what we really hope is a technique can help us to figure out the task mapping between the CPU and the GPU on heterogeneous systems. I have mentioned about two problems of current GPU programming. The first, the OpenCL is a low-level program language. Programming with OpenCL is not easy. Although OpenCL provides certain code portability, allowing a single application to run on different architecture, it may not provide performance portability, which means application may need to be retuned for different architecture. The other thing is the task mapping between different processors on your system is quite important if we want to get good performance. So here is how we are going to tackle this problem. We develop a compiler to automatically to explore the OpenCL data paradigm, the compiler convert the OpenCL parallel loops into OpenCL kernels and generates optimized OpenCL code. Currently, we focus on the OpenCL data paradigm and do not support the task paradigm. The compiler applies a set of data transformations to improve the memory behavior for your GPUs. We use the machine learning techniques to determine when and how to apply certain data transformation, because some of the data transformation may not always be beneficial. One of the key innovations of our approach is that we use machine learning techniques to automatically develop a model to determine which is the best processors on your system to use to give the best performance. So using our compiler, the compiler automatically inserts pre-built machine learning model into the compiler binary. When the program runs, the machine learning model uses the information such as the characteristic of the program, the program input, to predict which device, whether the CPU or the GPU, to use to run the code. The idea is pretty simple. If it is not profitable to run the OpenCL code on your CPU, then simply run the original OpenMP version on the CPU. So here is how the compiler works. The compiler takes in an OpenMP program. It translates the OpenMP parallel loops into OpenCL kernels, perform the optimization, generate OpenCL code.
Can you just say, you keep saying OpenMP without saying what the base language that OpenMP is on top of. Is this just OpenMP on top of C, or on Fortran, or on C++?
On top of C at the moment. Generate OpenCL code. So for each OpenMP parallel loops, we first outline the loop body. We replace the loop body with a function pointer. The function pointer can be either point to the OpenMP implementation of the loop body or our generated OpenCL code. So for each generated OpenCL code, we also collect a set of program characteristic, or we call it coder features. So at the coder merge stage, we put the original OpenMP implementation of the loop body, the generated OpenCL code, the program features, and a machine learning model which we pre-built offline, put all of them together into the compiled binary. So when the program runs, the machine learning model will use the program features to predict which device to use to execute a program. So if the prediction says CPU, then we simply run the original compile the OpenMP version on the CPU. Otherwise, we'll run the OpenCL code on the GPU. The coder translation process is rather straightforward. So we convert each parallel loop into a single OpenCL kernels. Currently, we do not split or merge kernels. We apply a set of transformation to improve the memory behavior. For example, we apply loop interchange to increase the memory coalescing. We also swap the index of the array. We perform the memory loader reordering, register promotion, and some very simple vectorization. Sometimes we also change the data structure. For example, we may change the data structure from array of structure to structure of arrays. What we found that the most important optimization under our settings is basically loop interchange and array index, which I'm going to talk in the next slide. So here, this is an example showing how the loop interchange and array index reordering can actually improve the performance on the generated OpenCL code. So the original code so on the top was written for CPU. It is a 3-nested loop. The outermost one, the index of the outermost loop is I. The second one is J. The third one is K. So this forms an index space of I, J, K. If we look at the loop body, the loop always access the highest dimension of the array. This has memory behavior as shown on the top right. As you can see, this this memory behavior is quite good for the CPU because it has good cache locality for each CPU thread. But it's pretty bad for GPU because we want all the GPU threads to access the consecutive memory address at the same time. On the bottom, the left bottom, I shows the code after applying loop interchange and index reordering. So we first apply loop interchange. We swap the index space from ijk to kji, and then we swap the dimension of the arrays. So from the previous highest dimension is now on the lowest dimension. So this gives us the memory behavior as shown on the bottom right. At this time, all the GPU threads access the coalesced memory at the same time. This significantly improves the performance. Here is a concrete example of how loop interchange and array index reordering can improve the performance. Here I show the two diagrams using NAS parallel benchmark called BT. So each diagram has 3 bars. The first bar is running the OpenMP version using GCC on an Intel Core i7 6-core processor. The second bar is running the OpenCL code on an AMD Radeon processor at GPUs. The third one is running the OpenCL code on an NVIDIA GeForce GTX 590, I think so. So the left diagram shows the naive translation. As we can see that the GPU has no advantage at all when compared to the GPU. However, when we apply the loop interchange and array index reordering, we can see that actually the GPU is quite good for the large data set, which is class 8. This time, both GPU outperform the CPU. However, for a small input data set, which is W, the GPU is still better than the CPU is still better than GPU. So the takeaway message here is that application performance actually depends on the right optimization, the program input, and selecting the right device is pretty important if we want to get the best performance. This leads to the second part of my talks, is how can we have an effective techniques to determine the best device to use according to program characteristic and runtime program input. What we do is we use machine learning to build a model. The model performs like a black box. So the model takes in the characteristic of your input program, and hopefully it can predict the right device, whether the CPU or the GPU to use, and so that we can determine which version of the code to run. Of course, the most important thing is to determine the code features. Since this is a compiler-based approach, we use some static program features of the generated OpenCL code, such as the computation to communication ratio, computation to global memory ratio, and the percentage of coalesced memory access. Of course, some of the feature value actually cannot be determined at the compile time. For example, the computation, you can think of it is a function of the loop iterative count. So to do so, we represent those unknown feature value as a symbolic precomputation of some loop variable. You can imagine the computation could be the number of static instructions times the loop iterative count. And when the program runs, we know those values. We simply instantiate to get the accurate program feature and provide the program features to the model, allows the model to give us a prediction. Once we have a way to characterize the program, we can start building the model. Building a model is rather straightforward. It can be done automatically. To do so, we have a set of training programs. Here we use a set of training OpenCL benchmarks from the NVIDIA SDK and some other benchmark suite. For each training program, we first extract the code feature. We represent those code feature as a set of feature vector. We run the OpenCL benchmarks on different devices, and this gives us which is the best performing devices. This gives us whether the GPU we can get any performance improvement and use the GPU. So once we have those results, we put the feature vector of each program and the best device together and give them to a learning algorithm. The learning algorithm will correlate the feature vector to the best device. This gives us a model. So in this work, we use a decision tree. So you can imagine the output is a decision tree, which is a number of if-else statements. Once we have the model, we can use a compile time and runtime. At compile time, we extract the feature of the generated OpenCL code. The unknown feature value will be represented as symbolic pre-computation, as I said before. So at runtime, the model will first update the feature value using some information we know when the program runs. And then those updated feature vectors will be given to the machine learning model, which is built into the program binary when we compile the program. And the model will predict whether we should use the CPU or the GPU to run the code. And according to the predictions, our small runtime will set the function pointer of each loop body to the corresponding version. So currently for the CPU, we'll run the OpenMP version on it. For the GPU, we'll run the generated OpenCL code. Here comes the experimental setup. We evaluate our approach on two GPU platforms. The first one is NVIDIA GeForce plus Intel Core i7 6-core multi-core CPU. The second one is an AMD Radeon graphic cards. And we have an identical Intel Core i7 multi-core CPU. We use the GCC to compile the program. It's run on Linux. And we use our compiler to convert the full set of NAS parallel benchmark into OpenCL programs. Those NAS parallel benchmarks are actually quite complicated when you compare them to any existing OpenCL benchmarks. Some program contains up to 66 kernels. This is significantly larger than any of the existing OpenCL benchmark that only contains 3 to 4 kernels. We compare our approach to the closely related work, which is OpenMPC, which this compiler converts OpenMP programs to CUDA program. It's done in Michigan University. We also compare our approach to the handwritten OpenCL implementation of the NAS parallel benchmark. This is done by a research group in South Korea. So let's first look at the result on the NVIDIA GeForce platform. Here we have 3 bars. The first bar shows the performance of running the OpenCL codes on the Intel Core i7 multi-core CPU. The second bar is GPU-only approach that always run the generate and optimize OpenCL code on the NVIDIA GeForce graphic cards. And the third one is our predictive model, or machine learning-based model. It predicts whether you should run your code on the CPU or on the GPU according to program characteristic and program input. So the x-axis here shows the performance of each individual benchmarks. We sorted according from the smallest input data set to the largest one. For some programs, because the GPU does not have enough memory to run the large input data set, so we do not include them in this diagram. The baseline is the single-thread execution of the OpenMP version on the Intel Core i7 processor. So if we look at the BT program first, what we found that for the small input data set, which is S and W, the CPU outperformed the GPU, which is not a surprise result because there's simply not enough parallelism to fully explore the GPU. However, for large input data set, we do see that actually the NVIDIA GeForce outperformed the CPU because there is more cores on the GPU, obviously. And we observe a similar result for benchmark CG. For EP, which is embarrassing the parallelizing benchmark, this time the GPU significantly outperformed the CPU. We get over 70 times performance improvement over single threads in execution on the CPU. For FTIS, which is kind of not very obviously, because this time the CPU outperformed the GPU because there's not enough parallelism. This is in particular for IS. And for LU, which is kind of a strange OpenMP program, it explores kind of pipeline parallelism. This cannot be easily implemented by an automatic compiler for the GPU. And our translation involves a larger communication between the host CPU and the GPU. Therefore, there's no performance improvement at all for GPU. And if a smart strategy would be to always use a CPU to execute the code. For NG, because there's a significant amount of indirect memory access of the original code, and this time again, the GPU is slower than the CPU. For SP, we found that for large input data set, the GPU outperformed the CPU. So on average, if we average the performance result across all the benchmarks, what I found is actually the OpenMP on CPU performs quite good. It achieves on an average speed up of 2.8 times. The OpenCL on the NVIDIA GPU achieve a speed up of 1.2 times. This is because it cannot get the performance improvement on several benchmarks. However, by selecting the right device to run the code, our approach achieves a speed up of 4.7 times, which is much better than any of the CPU or GPU-based approach. We also compare our performance to an Oracle approach, which we assume that the approach always picks the right device. So this gives us a kind of estimation of how good our approach to the best available performance by selecting the right device. So what I found is that it's not far from the Oracle. We achieve a 98% of the Oracle performance on this platform. So if we look at the AMD reading, we get similar results. For some applications, that the GPU is for some applications the GPU performs quite well, particularly for EP. For some others, it does not. On average, we get a speed up of actually no speed up for GPU on the AMD reading, because for the majority of their application, the GPU is not a best fit for them. For OpenMP, we get a 2.6 to almost 2.8 times speed up. And our approach again achieve a 4.8 times speed up, and it's not far from the Oracle, and only in one occasion, which I think is the FT on dataset 8, we make the wrong predictions, but the performance gets not far from the correct OpenMP, running the OpenMP version on the CPU. So our last comparison, we compare to state of the art, which is the OpenMP-C, which is compiler to translate the OpenMP program to CUDA program. We also compare our approach to SNU-MPB, which is a handwritten OpenCL implementation of the NAS parallel benchmark. This time we run the code on the NVIDIA GeForce platform because the CUDA can only be run on the NVIDIA platform. So what I can find here is that actually the OpenMP-C has no speed up for most of the application because it does not apply a certain data transformation, including array index reordering, vectorization, and memory reordering. And the SNU-MPB is quite good for many benchmarks, and in particular for LU, because they change the algorithm, they change the original implementation of the OpenMP version, and this time they are able to get the speed up on the GPU, but still the performance gets on the GPU is not able to beat the CPU. So on average, our approach is almost 1.63 times faster than the hand-coded version. So here comes a conclusion. We develop a compiler framework for explore the CPU-GPU heterogeneous systems. We applied a set of transformation to improve the quality of the generated OpenCL code. We use predictive modeling for task mapping at runtime to determine which is the best device to use on your heterogeneous systems. The key point is the model is automatically trained offline. You can imagine if you want to develop a compiler, you can build the models at the lab and ship the model to your customer. So whenever you want to target your compiler for new processors, the only thing you need to do is to rerun the automatic process, and hopefully the machine learning will give you a new model. So that's it. Thank you.
Okay, so we should have time for one or two questions. Or Jim wants to, thought you might.
Have you tried using the OpenCL system for the CPU?
No, we didn't.
Why not?
At the time that we did this work, the Intel OpenCL compiler was not available.
Okay. Do you not think that would be worth doing?
Yeah, I think so. Actually, there's some evidence showing that actually running the optimized OpenCL code on the CPU is better than the OpenP version because you can manually vectorize some of the code which cannot be done by using the OpenP pragmas.
And that leads me into my second question, which is that you didn't use the Intel compiler on the host, and that definitely vectorizes better than GCC. So there's potential there for improvement as well.
It could be, but what we observe is actually the performance improvement of GPU is around at least 2 times faster, so we don't think vectorization is going to help a lot at that case.
So hang on. I knew I wasn't going to get it that. If you're not vectorizing on the CPU, you're throwing away a factor of 4 per thread for double precision, something like that. So saying a factor of 2 is you're never going to get back a factor of 2 is simply wrong.
Yeah, actually we try to compile. Okay, so we have previous work that uses Intel compiler to compile the NAS parent benchmark. Overall, the result, Intel result is better than GCC, but it's not factor of 2. So.
Well, I'm not saying it would be a factor of 2, but I'm saying that
yep.
If you're going to compare with something, you should compare with the best.
Okay.
You're not.
That's why you compare the Intel compiler to an old version of GCC.
All right. That's a coffee time discussion. Who else? We had a question over here.
Thanks for the talk. The question is, I have first a comment, which is a generalization of Jim's comment, which is, I think, looking at the example transformation you gave, which is a semantically changing transformation, you're going to have to disable a whole load of your more advanced optimizations, which assume you're not making that sort of semantic transformation. So you're really wiping out your compiler on your host. But the second question is, I think your examples are all about how you speed up whole programs. Surely the interesting thing is when you take a program and put a bit on the CPU and a bit on the GPU. Have you actually gone down that route yet?
Okay, so I want to answer the first question. Actually, we didn't screw up the host compiler because the host compiler always compiled the original OpenP program. We only apply transformation to the generated OpenCL code. So that's the first question. The second one, yes, we did thought about it, but for the NAS parent benchmark, it's not worthwhile to do so because if you do so, run part of the kernel on the CPU and part of the kernel on the GPU, this will involve a lot of communication overhead between the host and the GPU, and this will kill the performance. But maybe for other applications, it's worthwhile to do so.
I wonder if you might be trying to reinvent the wheel, because there are plenty of examples of GCC where it actually does that partitioning for you and offloads to things like Neon co-processors for parallelism. So I think you might want to have a look in some of that work that's already been done.
Okay, thank you.
And just one more down here.
You mentioned that the machine learning technique you were using was a decision tree.
Yep.
Can you describe that decision tree? Can you show us how it actually works?
Okay, here's a decision tree. So we have a set of features. So it looks like an if-else branch. So we traverse the decision tree and you give us an answer whether you should run the code on the CPU or the GPU. So if we implement it, it looks like an if-else branch in your code.
Thank you. So we'll leave it in. Let's thank our speaker again. Thank you very much.
Thank you.